Just like we did in class just today, we're going to start to take a look at estimating roots. This video is going to be short. It's going to show a quick couple sample examples about estimating roots. Before we begin and go further on it, we're just reminding ourselves what these and what this chart is showing us. We have perfect squares being laid out in these columns listed in black. And again, a perfect square means that when you take the square root, every answer turns out to be a whole number. So when I say the square root of 100, it's a perfect square because the answer is 10. And remind yourself again, square root of 100 is the same as what number times itself equals 100. Well, that must be 10. So I'm finding square roots, I'm looking for what number times itself equals the number under the root. When we go to estimating roots, we're going to go beyond these perfect squares. We're going to start finding numbers under the square root that is not a perfect square. And let's dive in. I'm going to keep my perfect square chart as a helpful guide. I recommend having one of these in your photo roll, having one of these you can access until you have them memorized. Otherwise, this process becomes really long if you don't have these memorized. So once you are looking through these, we're going to start by looking at the example of estimating the square root of 31. And so first off, I'm going to start by having my problem listed just right here. And then I'm going to use my perfect square chart. And I'm going to make a quick number line. And when I do that number line, I'm going to do it in two parts. In this number line, what I'm looking for first is the perfect square that is lower than 31, but close to it. So lower than 31, but close to it. And here I'm stopping at square root of 25. If I go beyond, I'm at the square root of 36, and that's above square root of 31. So I'm going to stop at the square root of 25 because that's the closest square root below the square root of 31, the closest perfect square below our target. Then I'm going to go the one right above it. So the next perfect square that I have is the square root of 36 because that equals 6. So 36 is above 31, so that's what I'm going to write on my other side of my number line. Square root of 36. Now I'm going to solve both of those perfect squares. So I'm going to have an idea that I know that the square root of 25 is 5 and the square root of 36 is 6. These two numbers should be sequential, meaning that they should follow each other in a row, 5 to 6. There's no whole number in between. They should be sequential. This is where I make my number line, connecting 5 to 6. So I want you to kind of picture that here is 5, there is 6, and now we have that number line made. So now what I ask when I'm estimating this root is I'm looking for the closest integer. Integer just meaning that whole number. And I have an idea of what it's going to be between. I know this exists between 5 and 6. We practiced that before. But now I need to know which ones it's closer to. So now I look at the differences. So I'm going to highlight this line right here because this line shows the difference between 25 and 31. And so the difference between those is 6. There are 6 numbers in between 25 and 31. If I didn't know that, I would just do 31 minus 25. And that equals 6. So now I look at the other side, 31 to 36. 31 to 36 has 5 numbers in between it, meaning that the square root of 31 is closer to the square root of 36 because there's less numbers in between. So that tells me if I was looking at this would be 5.5 directly in the half. Somewhere in between 5 and 6 exists the square root of 31, and since it's slightly closer to square root of 36, I'm going to say that that number exists here. So what's the closest integer? Well, it's closer to 6. So my final answer, 6. And again, I'm estimating, so I'm going to put this little approximate sign. The square root of 31 is approximately 6. If I was looking to be really specific, I would probably give an answer closer to like 5.6 or 5.7. I know it's greater than 5.5 because that's right, it's above that halfway line, but I also know it's closer to 6. So looking at closest integer, 6. We're going to do one final example, and then we'll be done with these. These are just reference points, and again, using your notes from today. Our example pulls in, let's look at the square root of 101. So again, I'm going to add in our perfect square chart. And when I put in that perfect square chart, that's going to help me get my parameters. So my parameters are, again, I'm looking for the perfect squares that are both below and above 101. So scanning this chart, I'm going to end up at the square root of 100, which is below, and the square root of 121, which is above. So now I know off the top of my head that the square root of 100 is 10 and the square root of 121 is 11. Again, I have sequential numbers, so I'm just going to make my number line. And now I look for the differences. What's it closer to? The square root of 101 compared to the square root of 100 has a difference of 1. The square root of 101 connected to the square root of 121 has a difference of 20. That tells me that the square root of 101 is way closer to 10, or the square root of 100, than it is to 11, or the square root of 121. So my final answer here would be 10. What's the closest integer to the square root of 101? Well, it's 10, because it's super close to the square root of 100, and the square root of 100 equals 10. So we're going to use these to kind of estimate. And again, if I was looking at this exact halfway point, this would be where these two distances are exactly the same. And we really probably won't ever see that, but that's where I'd put that 10.5 number right in the middle if our distances between our two perfect squares were exactly the same. But we're always going to keep looking towards the nearest integer. So hopefully these videos help. Refer back to these if you need some extra assistance. Otherwise, check your notes.